All right, let's get started. Finishing up now, expected values, and then going on to variance. So, let's go back to our definition of expected value. Let's write that out once, just to remind us. What is the expected value of x by definition? Assuming we already have some sample space S and P. So assume I tell you some sample space S and P, and some random variable x, I define it for you. What is the expected value of x by definition?
The sum of s and s.
The sum for every little s and big S.
Yeah, of x of s.
Of x of s.
Plus p of s.
Times p of
I mean,
s.
p of, yeah, times p of s.
Times p of s. There we go. That's how we calculate the expected value. Now we proved this theorem last time, that the expected value, if I have x and y as random variables defined on the scene, maybe s's numbers 1, 2, 3, 4, x doubles them, y squares them. Something like we did in a homework problem, right? Mm-hmm. Then how would we calculate the expected value of x plus y?
The expected value of x plus the expected value of y.
Yeah, let's rederive this proof really quick to remind us of how this worked. So writing out just using the exact definition, here's our expected value of x, there's its exact definition. Let's look for the expected value of x plus y. What is this going to be equal to? This is going to be the sum. I'm going to stop writing for every little s and big S and assume you know that that's what we're summing over. It's going to be a sum for every little s and big S of x of s plus y of s all times p of s. It's plug in s to our random variable and then multiply it by p of s. So this is just using that definition. We just replaced x with x plus y. So rather than x of s, we had x plus y of s. Make sense? So far I just plugged into the definition. Now, our sum is like this, by the way. All those terms are included in our sum. Now, I'm going to distribute p of s to each of these. So this is equal to the sum of x of s times p of s plus y of s times p of s. Just distributing this into this, right? You with me? And now I can separate the sum into two separate sums. So this is equal to the sum of my x of, oh yeah, we can do it. My sum of all my little x of s's times p of s plus my sum of all my y of s's times p of s. With me? And then what is this? What is this the definition of?
The expected value of x.
This is the definition of the expected value of x. And what is this the definition of?
Expected value of y.
The expected value of y. And so we just really showed that the expected value of x plus y is equal to the expected value of x plus the expected value of y. Where was this really, really, really useful? In calculating something like the expected value of rolling 2 die. If I'm rolling one 6-sided die, what's its expected value? 3.5 or 7 halves, right? For rolling one die. And we can calculate this by hand. It would just be doing this for the 6 possible options. 1 times the probability of a 1, or 1/6, plus 2 times the probability of a 2, or 1/6. 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. And you add that all up and simplify it, and you're going to end up with 7 halves. That one's really easy to calculate by hand. Now if I ask you to calculate, all right, what's the expected value of rolling 2 dice now? Well, if we use this definition, we'd have to add up 36 terms. That sounds like a nightmare. Instead, we can say, well, I know the expected value for 1 die is 7 halves, and so the expected value for the 2 die is just adding them together. It's just 7. You see the value there?
It's just
Why is it not 14 halves?
15 halves.
I can never answer that. All right, so that was the use case of something like that. Now, our next one was the expected value of some constant times x. Proving that that's equal to just that constant times the expected value of x. So what if I said, you and I were going to play a game. When you roll a die, so you have one six-sided die, when you roll the die, we're going to double your roll, and that's your actual roll. So if you roll a 1, we're going to call it a 2. If you roll a 2, we're going to call it a 4. You with me? What's the expected value now of your rolls? Do you understand the game?
Yeah. Wait.
Okay, we're playing a game. First version of the game is you have a six-sided die. You get to roll the die. Whatever number you roll, I give you that much money. If you roll a 1, I give you $1. If you roll a 6, I give you $6. You with me? What's your expected value in the game?
$3.50.
$3.50, right? That's how much you expect to get if you play this game. Now what if I say, okay, if you roll a 1, I'll give you $2. If you roll a 2, I'll give you $4.
So 7.
If you roll a 6, I'll give you $3, ... If you roll a 6, I'll give you $12. Now how much money do you expect to get if you play the game?
7.
$7. What did you do? You multiplied by 2. You said the expected value of 2 times x, my random variable, should just equal 2 times 7 halves. And now we'll prove that you can always use that thinking in general.
Didn't we prove all these things?
Yes, we proved it last time. Just re-dipping your toes in to get you comfortable with the notation all over again. So the expected value of c should be very clear. X is a random variable, that's a function. C is some constant, like 2. So c is just a number. X is still our random variable, a function. So c times x is equal to, by definition, what is it? It's going to be the sum for all little s and big S of c times x of s times p of s, right? That's just using the definition for expected value. Have I lost you?
No.
You good? That's just using its definition. Wonderful. Now we have c in a bunch of terms, we can just factor the c out of the sum. This is just a sum of a bunch of terms, all of which have c. If you have c times a1 plus c times a2 plus c times a3, you can factor the c out of the sum and just call it c times a1 plus a2 plus a3, right? So that's all we're going to do. We're just going to factor the c out of the sum. So this is equal to the sum. This is equal to c times the sum of x of s times p of s. But what is this a definition of?
Expected value of c times x.
Yeah, but just this piece right here is
Expected value.
the expected value of x. So this is just c times the expected value of x. Nice and easy, right? And then we had linearity. Linearity, if you have a constant a times your first random variable plus a constant b times your second random variable, that's equal to, and you take its expected value, that's equal to a times the expected value of x plus b times the expected value of y. We call that linearity. This is just using this and this theorem together. This theorem and this theorem together give you this. So we won't bother reflushing that one out. Let's move on to the next one. The expected value of x times y is equal to the expected value of x times the expected value of y. You remember doing this one?
Yep.
Ish. Let's prove this. Should we prove it? You remember the proof already, so we don't need to do this? Or you don't remember the proof?
Prove it.
Prove it. Let's prove it. We can't prove it because it's false.
Boom. That's why I said ish.
Ish. All right. So let's do an example to show us that this is false. Going back to our counter example. We said S is going to be, we're going to do the sample space for flipping a coin twice. So S is going to be heads, 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 tails, tails, heads, tails, tails. And the probability of each little S, we're going to say it's a fair coin, so it's just 1/4. We made X of H is going to be the number of heads in each flip.
Okay.
Okay? So X of H is equal to, when you give it heads, heads, spits out 2. When you give it heads, tails, spits out 1. When you give it tails, heads, spits out 1. And when you give it tails, tails, spits out 0. With me? And x of t, same thing. That is just number of tails. And I'm not going to write it out.
Okay.
So x of heads gives us the number of heads in a foot. X of t gives us the number of tails in a foot. Okay. Let's calculate the expected value now of x of h.
Okay.
What is that going to be equal to?
1.
That is going to be equal to the sum for all little s in big S of x of s times the probability of that, which is going to be, what do we get when we plug this into x of h? Sorry, look up here. What do we get when we plug this into x of h? 2 times, now, its probability. 1/4. Plus, what do we get when we plug this in? 1 times 1/4. Plus, what do we get when we plug this in? 1 times 1/4. And what do we get when we plug this in?
0.
0 times 1/4. Okay, so the expected value of x of h then is equal to what?
2 times 1/4 plus 1 times 1/4.
You have 2/4 plus 1/4 plus 1/4.
1.
4/4 or 1.
Yeah.
Wonderful.
Wonderful.
Now let's figure out the expected value of x of t.
This is also wonderful.
What do we get when we plug this in for x of t? 0 times its probability 1/4. Plus, what do we get when we plug this in?
1.
1 times 1/4. When we plug this in, 1 times 1/4. And then finally, when we plug in the last one, 2 times 1/4. Okay? And so when it's all said and done, the expected value of x of t is equal to 1. Perfect. Now let's figure out the expected value of x of h times x of t and see what we get.
1.
So, let's remind us of what exactly this is going to be. This is going to be the sum for all little s in big S of x of h of s times x of t of s times the probability of s, right?
Yep.
So let's calculate that. What do I get when I plug in HH to this?
2.
What do I get when I plug HH into this?
Does.
2. Right? What do I get when I plug into this?
Well,
0.
0. What do I get when I plug into this?
1/4.
1/4. So 2 times 0 times 1/4 is a half.
0.
0. 0 times anything is always 0.
Um,
Yeah. Okay.
It's okay, just cancel out the 2 and these add the 1/4.
Alright. Now let's try it again. Now we're plugging in HT. We're plugging in our next one. We're plugging these 4 things in for each little s and big S. We're calling each of these our little s. When I plug HT into this, what do I get?
1.
1 times
1.
times
1/4.
1/4.
equals
1/4.
1/4. Plus, next, I plug in TH into it.
1. 1. 1/4. 1/4.
And finally,
Zilch.
2 or 0.
0 times anything is 0. Right? And this whole thing comes out 1/2.
Yep.
Which is not the same thing as 1 times 1. The expected value of this times the expected value of this is just 1, yet the expected value of their product came out to 1/2, not 1.
That's so weird.
So this does not, in general, work. It does work if x and y are independent. If x and y are independent variables, then the expected value of their product is the product of their expected values. So that will be our next proof here. Hopefully I can do this on the fly. Should have reviewed it. Alright. Proof. Let SP be a sample space with xy as real independent random variables. Then the expected value of x times y is equal to the expected value of x times the expected value of y. That's what we're going to try and prove. Ooh. Okay. So we'll assume all that and just jump right into the equation part. So let's look at the expected value of x times the expected value of y. So the expected value of x times the expected value of y is equal to, now we have two ways that we can write this. We can say that this is equal to the sum for all little s and big S of x of s times y of s times p of s, and that would be true. But we're going to use a theorem from last time that we used, which was another definition of expected value. Maybe you remember this, hopefully you do. The expected value of x is also equal to the sum for all a in R of a times the probability of a. That x is equal to a. And this was just a regrouping of the terms. I'm going to take all the times that made x equal to 1, see how often that happens, and multiply it by 1. Then I'm going to look at how often x is equal to 2 and multiply it by 2. Then I'm going to look at all the times x is equal to 3 and multiply it by 3. And maybe we have some numbers that x could never be. Maybe, for example, x can never be 10. This still says take the probability that x is equal to 10, multiply by 10, and add it to our result. But that would just come out 0 if our random variable never spits out that number. So you're just adding a bunch of zeros. So it doesn't matter. You with me?
Mm-hmm.
So this is a definition that we're going to be using up here. So this is equal to the sum for all a in R of a times the probability that x times y is equal to a. Okay. Well, if x times y is equal to a, then x times y, x had to be equal to some real number, and y had to be equal to some other real number, such that their product came out a. So there had to be two real numbers, b and c, that x and y were equal to, such that their product equaled a. You with me? So I'm just breaking them into their product. If I know that x times y is a, then I know that x and y had to be two numbers such that their product is a. I'm just going to call them b and c. Okay. So this is equal to the sum for all b, c in the real numbers such that b times c is equal to little a of b times c times the probability that x is equal to b and y is equal to c. You see how that's saying the exact same thing? If x is equal to b and y is equal to c, and I know that b times c is equal to a, then x times y is equal to a. So it's the same thing as what this was saying. If I know that b and c are real numbers such that the product is a, and x is equal to b, y is equal to c, then x times y is equal to a. So this is saying the same thing as this. And b times c is obviously the same thing as a. You have my substitutions there?
Yeah.
Just renaming it.
Just renaming it. Now I'm going to split it up. I'm going to pick my b first, and then find the corresponding c. So I'm going to say, in other words, I'm going to sum all my terms with the same b first. So I'm going to say for each b in the real numbers, then I'm going to go ahead and find the corresponding c. For the c in the real numbers, then we have b times c times the probability that x is equal to b and y is equal to c. You with me?
How does that sum work?
Just going to pick my b first, then choose my c.
So you're
The sum of the sum.
Yeah, it's just a regrouping of sums. So we have a bunch of sums that we're also summing together. So this has a bunch of terms.
So this is validate.
So it's just basically adding parentheses.
Okay.
Oh.
Pick your b, and then you have a bunch of inner sums. Rather than just having all my terms summed up like this, I'm coming through and I'm putting parentheses everywhere where our inner terms were using the same b.
Supposedly simplify it.
Supposedly. Doesn't seem like it's simplified yet, but you'll see. The point is the b is chosen out here, so inside of here, the b is now going to be a constant. If all these had the same b, sorry, we used a little b there, should call it a1 plus a2 plus a3. If all these three terms each had the same little b that they were using, then we're grouping all of them together, and so in this inner grouping, we're always using the same little b because that was chosen for the outer grouping. So this might be all the ones where b is equal to 1. This is all the ones where b is equal to 2, etc. If they represented expansions of this. Just a regrouping with parentheses. But now we're also going to use the information that we know. I know that x and y are independent random variables. What does it mean for them to be independent? If x and y are independent, then the probability that x is equal to a and y is equal to b is equal to the probability that x is equal to a times the probability that y is equal to b. That's by definition what it meant for them to be independent. So I can replace x is equal to b and y is equal to c with the probability that x is equal to b times the probability that y is equal to c. So that says the same thing as the probability that x is equal to b times the probability that y is equal to c. And it's being able to go from this step to this step that's then going to allow us to separate it and get a product of terms like that. That's why it had to be independent. It means that we can go from this to this. Anyways, so now let's continue working with it. So now all these inner terms are using the same b. So b is a constant inside this inner sum. So I'm going to factor the b's out of this sum. So this is equal to the sum for all b in R. Put big parentheses here so that we are keeping track of everything happening. Of b times the probability that x is equal to b, all times the sum for c in R of c times the probability that y is equal to c. And we're summing each of those up. Pick a b, and then we evaluate our c's. Same thing we were doing up here. We're just factoring out this inner sum, these two terms, since they don't depend on c. They only depend on b. So once our b is chosen, they were already chosen for the entire sum. Does that make sense? Now, this sum right here is the same regardless of what b is. So now I'm going to factor this whole sum out of each term in this sum, which then splits it into a product of two sums. So this is equal to the sum for every b in the real numbers of b times the probability that x is equal to b. And now, that's like this, times the sum for every c in R of c times the probability that y is equal to c. Okay, let's write this out. So I'm going to use b1, b2, b3, b4 to represent terms in this sum, and c1, c2, c3, c4 to represent terms in this sum. So before, writing it how we have it up here, we have b1 times c1 plus c2 plus c3 plus b2 times c1 plus c2 plus c3 plus b3 times c1 plus c2 plus c3. That's looking at it this way. Pick your b, then do all the c's associated with that b. Your next b, pick all the c's associated with that. And dot, 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 who knows how long that goes on, right? You with me?
That part makes sense.
Okay, now notice that this c sum is the same in every term. So factor it out of each term.
Just adding b's.
Right, so then you have the b1 plus the b2 plus the b3, all times what we factored out, which was a C1 plus a C2 plus a C3. That's what we're doing.
So a summation theory or summation that would follow the same like distributive rules.
Yeah, it's identical. This is doing the exact same thing as this. This was just a case where we were adding up 3 terms. Here we don't know how many terms we're adding up.
That C in R should be squared. It should have two summations on it.
C and R. This, up here, it's a sum in a sum.
Okay, take the sum and you have to multiply.
So
by
that's the
that,
same as
multiply
this.
by B. Yeah, okay. Makes
This
sense.
one's the same as this,
Gotcha.
where you have an inner sum happening inside of an outer sum. So you have an outer sum of a bunch of inner sums. And then we factor all those inner sums out, and it gives us now a product of 2 sums.
Yeah.
And now, once you have a product of 2 sums, notice, what is this the exact definition of?
Then multiply.
Well, this right here is now the expected value of x.
Value of
And this right here is now the expected value of y. Using our second definition of expected value, not definition, but the theorem we proved, that the expected value of x is equal to the sum, here's the way you saw it, for all a and r, of a times the probability that x is equal to a. That's exactly what this is for x, just as b's instead of a's for the variable. That's exactly what this is for y, just as c's instead of a's for the variable.
Is there any chance this question's on the quiz?
On the test?
Yeah.
Not this test, but another one.
No. No, the reason I try to force you to sink your teeth into this is because if you kind of get in the sums here, you're going to be okay with summation notation for a while. Because this is a pain. Right. So it's supposed to be a pain. It's the way it goes. You know, it's a struggle, it's a struggle, it's a struggle until you get it. And then you get it. And then suddenly you're like, why do you keep repeating yourself? I get it. That's the way it goes. So, gotta start struggling before you start getting it. We did that. We already talked about that example.
We might want to start a test.
We already did that. We're not doing it.
We're not doing a test this week?
No. We'll do it next week.
Why?
I just wanted you guys to come to class with your homework done.
We're going to be completely forgotten on everything.
Good. Now you have to review it twice. It's amazing. All right. Next.
Why?
So that you could experience that wonderful relief. Isn't that wonderful? You're
No.
welcome.
Yeah, we should do this.
The experiences I come up with for all of you.
That's just stressing now.
Well, before.
No, it's stressing now.
Oh, now you
I
feel
was
stressed?
in relief, and now I'm stressing.
Oh. Well, all right. If you're getting stressed about something, may as well be math.
That's a fair point.
Okay, next one. So now we're going to move on to another concept now called variance. Now, intuitively, variance tells us how spread out our data is. Intuitively, variance tells us how spread out our data is.
So like outliers?
Oh, wait, we're not moving on to variance yet. We have one more example. One more example of a use of expected value is finding a midpoint. Common physics problem. If I've got, some board, and I've got some mass here, some mass here, some mass here, some mass here, where should I put my pivot point so that they perfectly balance each other out? That make sense?
Yep.
Let's do a problem like that. And we'll use expected values to figure out the problem. Here's a way to interpret the problem. So S is going to be the numbers 1 through 10. We're going to put 10 objects on our board. P of S is going to give us the weight of each object. Each object has weight 1/10. 1/10 what? Doesn't matter. 1/10 a ton. And X now is going to tell us where those weights are on the board. So we've got our board here. We go and we mark it off. We're going to call this point on the board 0, 1, 2, 3, 4, all the way up to 10. And X now is telling us where each of the weights are. The first weight is at position 1. So we have one weight here. The second weight is also at position 1. The third weight is also at position 1. The fourth weight is also at position 1. The fifth weight is at position 2. The 6th weight is at position 2. The 7th weight is at position 8. And then 8, and then 8, and then 8. So the question is, so now this is on some board, like this. Where should we put our pivot points so that these are exactly balanced out? Where is, in some sense, the middle of all this?
3.5. 4.
3.5.
3.5, 4, 5, who knows? Rather than guessing, let's just calculate it.
Okay.
The answer is the expected value. And so, let's write this a little bit smaller so we have some space. We just need to figure out the expected value of x. And that is going to be equal to, we get a 1. How often do we get a 1?
4.
We'll think about it in terms of expected value of x is equal to the sum for all a in R of a times probability of x is equal to a. So we'll just think about that way. So we'll do 1 times the probability that x is 1. How often does that happen?
4 ones.
4/10 the time,
Yeah.
right?
Yeah.
Yep.
Plus 2 times the probability that x is 2. 2/10 the time. Plus 3 times the probability x is 3, never. Plus 4 times the probability x is 4, never. Plus pi times the probability x is pi, never. Ignore all our zeros and skip straight to the ones we care about. Plus 8 times the probability x is 8, which is
4 tenths.
4/10. Which is equal to, let's do it in terms of tenths. 8 times 4 is
32.
32, plus 4 is,
36.
plus 4 is
40.
40. So we got 40 tenths, which is equal to
4.
4.
Right
We
on.
put our pivot right at 4, and that would perfectly balance it.
Just guessed.
It's in some sense the perfect middle. Physics way of saying it is that's how we would find the center of mass of the system. Finding a center of mass is finding an expected value. Mathematically speaking, they're logically equivalent. Okay, so that was the last one. Now we'll talk about variance and how spread out the data is. So, we've got some sample space, some probability function. What are they? I don't know. I don't care. We've got 3 random variables here, x, y, and z. X spits out a 2 50% of the time and a negative 2 50% of the time. Y spits out a 10 0.1% of the time, a 0 98.8% of the time, and a negative 10 0.1% of the time. Z spits out a 3 1/3 of the time, 0 1/3 of the time, negative 3 1/3 of the time. We want to know which of these is the most spread out data.
What does that mean?
Yeah, we need to come up with a notion of what spread out means, but hopefully, to some extent, our notion of spread out appeals to our intuition as well.
It's Z.
So let's look at a picture of each of these to get a sense of, I think in the book this was supposed to be 5 and negative 5. No, I'm seeing that. Probably will help the math be simpler. I don't know. But let's look pictorially at each of these really quick. So x here, when we look at x, so here's negative 2. Let's create a full number line for each of these. So we have negative 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and this was negative 10. All right, so when we look at x, we'll plot x's data up here. 2 and negative 2. We'll plot x's data up here. X looks like we get 2 like this, and we get negative 2 like this. Same number of 2's and negative 2's. Here's x's data. If we were to plot it at least something like that. I'm just drawing it clear up here so that we don't draw on our number line. If we look at y's data is all around 0. We keep getting 0 over and over and over again. So it's just basically a solid line here at 0 with occasionally every now and then we get a 10 and we get a negative 10. So there's y's data. So this was x's data, here's y's data. Z's data is we get a 3, or we get a 0 1/3 of the time. We get a 5, 2, there's my 2. Oops. Pretend that lined it up. 3, 4, 5. We get a 5 1/3 the time, and we get 3, 4, 5. And we get a negative 5 1/3 the time. Here's Z's data. So X's data looks like this, Y's data looks like this, Z's data looks like this. Which of these data are the most spread out intuitively?
Intuitively it's Y.
Intuitively it's Y. Y is almost always in the middle. It's hardly ever away from exactly 0.
It's just what my intuition said.
That's what your intuition says? Okay, before we continue with that, let's notice something about these data really quick. Let's look at their expected value of each one. So if X gives 2 half the time and negative 2 half the time, what's its expected value?
2. 0.
0. Let's say that in terms of a game. We're playing a game. Every time you flip a heads, you give me I give you $2. Every time you flip a tails, you give me $2. On average, how much money do you make?
Depends on who's playing.
0.
0.
0. Right?
Right.
Making intuitive sense? Or, just do the math. 2 times 1/2 plus negative 2 times 1/2 is 0. Okay, what about this one? We're playing a game. You're going to roll 1,000-sided dice. If you roll exactly 1,000, I give you $10. If you roll exactly 1, you give me $10. If you roll any other number, no one gets anything.
Deal.
What's the expected value?
10.
0. Final game, we develop a 3-sided die,
The expected value is also 0.
and it's a fair die. Every time you roll 3, you get $5. Every time you roll a 2, nothing happens. Every time you roll a 1, you give me $5.
So they're all spread out the same.
So, no, they all have the same expected value.
Expected value is
So notice that the expected value of all these is 0. Or in other words, all these center around 0. 0 is somehow the middle of this data. 0 is the middle of this data. And 0 is the middle of this data. You with me? Now, which data is the most spread out? Well, in order to answer that, we need to come up with a notion of what it means to be spread out. And just a quick reminder, this mu symbol is often a shorthand for the expected value of x. So mu and expected value of x, I'll be using that interchangeably.
Oh.
So how might we figure out how spread out some data is? You might say, let's just look at how far the data is from its middle point. Because ideally, a data that has no spread outness is where all the data is exactly at the middle, right? If all the data is exactly at the middle, then there's no spread outness to it. So let's just look at each data point, like this one, and let's look at how far away it is from the middle and see how often that happens. So this one's 2 away from the middle 1/2 the time, and it's negative 2 away from the middle 1/2 the time.
So it's X. X is
Right?
the most spread out.
So that's one way we could think about calculating its spread outness. We can say, what does it mean to be spread out? We can take each data point, x of s, and we can subtract the middle point away from it. So a number minus the middle point, this gives you the distance between the 2 points, right?
Yeah.
Is that absolute value or anything?
No, no absolute value in here.
What if it's like that and it's a -2 distance?
Exactly. So, you're probably seeing a problem already that we're going to run into. So you take the data point minus how far away it is from the middle, and then multiply it by how often that happens. Does that make sense?
Yeah,
You follow that?
I do.
You sure?
We'll see.
We'll see. Okay, let's just follow this out for a second then. So let's say that we use as a spread outness, we use the notion, we'll take the data point, how far it is away from the middle, and just multiply it by how often that happens. And that will be how spread out the data is. Well, let's do a little bit of math on here. I'm going to distribute the P of s into each of these. So when I distribute that in, we're going to have the sum of x of s times P of s minus mu times P of s. Right? That's just distributing that into both those terms. You with me? Now the sum of all those differences, the sum of all these terms plus these terms, I guess you could think about, is the same as first add up all these terms, then add up all these terms. So I'm just going to break it into 2 sums.
Yep.
So add up all these terms first, and then we'll add up all these terms. Notice that those terms are all negative terms, but so we're adding up all negative terms. You with me?
Subtracting, yeah.
while adding up a bunch of negative numbers, and then we can subtract it when we're done, because it will come out negative. Okay, anyways. Now, what is the sum of x of s times p of s for every little s and big S? What's this a definition of?
The expected value of x.
That's the expected value of x. Now, for this sum over here, I'm just going to factor the negative mu out of each of these terms, because negative mu is just a constant. So I'm going to factor that out of the sum. So here's my negative mu factored out, and we're adding up all the p of s's now. What is the sum of all our probabilities?
1.
1. If you add up all the probabilities in your probability function, you always get 1. So e of x minus mu times 1. E of x minus mu times 1. Or e of x minus mu. What is e of x minus mu?
I don't know.
What is
it's
mu?
0. It's 0.
Mu is shorthand for e of x. What's e of x minus e of x?
0.
0. So if we try to use this notion of spread outness, we'll always get 0.
So why are we learning about something that always gets 0?
Yeah, why are we learning about something that always gives us 0? I was trying to give you, here's intuitively what you might think, and that's going to come out 0. Why is it always going to come out 0? Probably what Chandler was hinting at before. Every time you got a data point to the right, which is going to give you a positive number, you also have the same amount of data points to the left, canceling it out. If you're talking about your distance from your middle point, think about on the teeter-totter, all the weight and how far it is over here, any weight we have on the right-hand side is always going to be perfectly canceled out by the weight we have on the left-hand side. And when we add it all up, add up all those differences, it's always going to be 0. So that doesn't work.
So none of them are more spread out.
Well, this just isn't a good way to give us a spread outness. And the problem is that this can be both positive and negative. And Jeremy was suggesting something that could be used. We could say, rather than calculating the distance, we could do the absolute value of the distance. Then it would always be positive.
Yeah, but it'll all still come out 0. So.
Now,
Oh, if you make mu pi positive.
if we did the absolute value of that difference, that's always a positive number. We're no longer adding a 2 and a negative 2. Instead, we're adding a 2 and a 2. That's one way to do it. And that would be a fine way of coming up with the notion of what we mean by spread outness. It's not the one that's chosen. The one that's chosen is to square the distance. And then that will also always give you a positive number.
Why is that one chosen? That looks like a hassle.
The other reason that that one's chosen, well, first off, no. Working with squared is way easier than working with absolute value. Because absolute value, you always have to keep track of the positive and negative case. Whereas squared's just squared.
Flipping a sign is not very hard.
It is
I
much
see what
easier
I see what
for you to think about x squared is less than 4 than for you to think about the absolute value of x is less than 4. It's easier for most people. And then if I ask you to do something like find out where this is true, x squared is equal to 4, that's probably easier for most people to figure out than something like the absolute value of x minus 2 is equal to 4. So, in general, it's easier to work with the squared than absolute value. But besides that, what this also does is says if the data is a little bit, if the data is really small, squaring it doesn't really matter, right? If your difference is small, squaring it doesn't really matter. When you square a small number, you get an even smaller number. What's 1/2 times 1/2? 1/4. When you square a small number, it gets even smaller. So if the distance is really small, we're saying we don't really care about small distances as much. And if the distance is really big, what's 10 times 10? 100. So when you're squaring numbers, small numbers, they just get smaller. When you're squaring big numbers, they get much bigger. So this is saying we really care about it if the data is far away, and we really don't care if it's really close. And it helps you account for that by squaring it. So there's 2 reasons to square. 1, keeps it positive. 2, gives you more emphasis on data that is far away and less emphasis on data that's already close. Those are 2 rationalizations for picking a square. And so that's exactly what we mean by variance. By definition, the variance of x is equal to the expected value of x minus mu squared, which is what this is. X of s minus mu squared times p of s. That's our definition for variance. You with me?
So variance just means spread out.
Variance is a notion of how spread out the data is, but here's its exact definition. And as we talked about, there might be a few different ways you come up with the notion of spread outness.
So it's
Here's the one that's chosen for what we mean by variance. So variance is a common term that people talk about relative to data. They say, what's the variance of the data?
Well, don't we want to use that graph line and figure out which one's more spread out?
Oh, that picture there? We're going to calculate their variance now over here. So can I still see the top? I think I can. All right, I think we're good. So let's calculate the variance now of each of these, so you know how to calculate variance. Da-da-da. So now looking at our exact definition and looking at the data right here, we're using this x, y, and z. Let's calculate the variance of x, the variance of y, and the variance of z. And see which of these are the most spread out. So variance of x. What is the variance of x? Tell me exactly what to write.
The summation sign
The sum,
from S to small s to big S.
we'll assume that it's always the sum of that and just keep going.
Okay, parenthesis x of 2.
X of little s.
Oh, yeah. So we're just repeating that minus mu. Square that times 2s.
Times p of s, right? Now in our case, x of s can come out two things. It can come out 2 and negative 2. So this is going to be equal to 2 times, or 2 minus, what's mu going to be in our case?
Mu 0.
Mu is 0, so we won't bother with the minus 0 there. 2 minus 0 is just 2 squared times what's the probability of 2?
50% chance.
1/2. And then we're going to do plus, what's our other x of s?
Negative 2.
Negative 2 minus 0 is still just negative 2 squared times 1/2, which is equal to
4.
4. We have 2 squared is 4 halves, plus 4 halves is 8 halves, or in other words is 4. So this data obviously has a spread outness of 4, right?
Variance.
That's its variance. Notion of how spread out it is in some sense. All right, now let's do y. Do we expect y to be more spread out or less spread out than x?
Way more.
Way more spread out, right?
Yeah.
No, it should be way less spread out. Almost all the data is together, with very occasionally we have a random outlier. We don't care that much about random outliers
Okay,
if there's only a very small amount of them. But let's calculate its actual spread outness now. So this one is going to be, we won't bother rewriting the equation here, we'll just keep plugging into this.
Okay.
What's my first x of s going to be?
10
10
squared.
squared minus,
It's still 0.
right, so 0. So we can just do the 10 squared times, how often does that happen?
0.1%.
1/1000, we'll say,
Okay.
just to keep it clear. Plus, our next one is 0
So just ignore that.
times 988 over 1,000.
That doesn't make sense.
This should be a 9.
Yeah.
Thank you. 99.8.
There we go.
But, so that's going to be 0 times, just write it,
Well,
998 over 1,000. We know it comes out to 0, but just to see us explicitly using the formula. And then plus,
100,000.
plus negative 10 squared times 1,000. Right?
Yeah.
Yep.
Okay, and what do we get? We get 100 over 1,000 plus 0 plus 100 over 1,000. Or 200 over 1,000, or 0.2.
1/500.
1/500. 0.2. Same thing.
Whoa, that's a big
No,
difference.
no.
Oh, whoa. I meant of a percent.
Yeah, what? That's good.
Oh, wait, no, I did that right.
0.02. Or 0.02.
No, he's right.
0.2.
One.
This isn't a percent. 0.2. That's
That's
right.
100.
That's a spread out.
You're right.
Yes.
That's a big difference.
No. Because that first one came out to be 8 over 2.
What's 100 divided by 1,000?
100 divided by 1,000 is a tenth.
What's 200 divided by 1,000?
2 tenths.
So now I got 1 over 500.
Okay.
That's just reducing it.
Right. Is it over 500? And I'm instantly thinking, oh, that's 0.02 of a percent. Or 0.2 of a percent. Anyways, doesn't matter. Doesn't matter. We were thinking weird. Okay, so that is a much smaller number than that. So this data is much less spread out than this data. Yeah, it goes all the way to negative 10 and 10, but it hardly ever does that. Most of the time, its data points are right smack in the middle. Whereas over here, we're never at the middle. All right, now let's look at z. Now z goes all the way to 5 and negative 5, but it still has 1/3 of its data right smack at the middle. Do we think that this is going to be more spread out than x or less spread out than x?
Less.
Probably a little
More.
bit more.
Probably a little bit more. Why should we be thinking probably a little bit more? Because a 5 is a much bigger number than 2, and we square the distance.
Yeah, but 0.
This is going to have 1/3 of its data being measured at 25, or 5 squared,
That is true.
and another third of its data being measured at 25, and a third of its data being measured at 0, whereas this just had half its data being measured at 4 and half its data being measured at 4.
So it's going to be less.
So it's going to, z is going to be more.
More.
1/3 of its data is going to get a score of 25, a distance of 25.
Okay.
Anyways, let's go over the numbers. So we have 5 squared times 1/3 plus 0 squared times 1/3 plus negative 5 squared times 1/3, right?
50 thirds,
Which is going to be 50 thirds.
which is going to be very slightly more than 4.
Way more than 4. What's 16 times 3?
Whoa, how'd you do that math so quick?
50.
48.
50.
48, so this is going to be, so that's a remainder of 2. So this is 16 and 2/3 if you want to think about it in an awful way.
Yeah, 16 2 3.
Or 16.666, blah, blah, blah.
Yeah, that's an entire order of magnitude off.
Yeah, definitely not close to 4. How did I do that math so quick? I know that what's 17 times 3? 51. Subtract 1. That's the way I thought about it.
17 times 3.
Okay.
Ask me how I thought about it. That's how I thought about it.
You just have memorized that 17 times 3 is
We
51.
just gotta logic it.
Well, it was just the first thing that occurred to me.
17 times 3 is
17 times 3, natural.
It's like if you look at a wall and you end up looking at that brick first, why that brick? I don't know, I turned my head, that's the brick I saw. I looked at 50, 3, and I'm like, 17's 51.
Right, okay.
Alright, so there we go.
Okay.
So this one is the least spread out, second least spread out, this one is the most spread out.
which is weird.
Alright, let's try this again.
Let's go.
Let's now
Right.
try the variance for rule, huh?
I was right. In the beginning, I said Z was the most spread out.
Okay. Z is the most spread out, yes. Okay, so now we're going to talk about rolling a single die and calculate the variance for that. So single die rule, we're going to roll a single die, calculate its variance.
Okay.
Alright, so let's do that. How do we calculate its variance?
Take the summation notation.
Right, so we're going to do the sum for all little s and big S. So it's going to be 1 through 6 of x of s minus mu. What's mu in our case?
3.5.
Squared times p of s. Right, we already know that mu, or the expected value for rolling one die, is 7/2. We've already calculated that before, right?
Yep.
So now let's calculate the variance. So the variance is equal to, we're just plugging in 1 through 6. So it's going to be 1 minus 7/2 squared times, what's the probability of rolling 1?
1/6.
1/6. Plus, then we're going to do 2
Minus 7/2.
minus 7/2
Squared.
squared
Minus 1/6.
times 1/6
Dot, dot, dot.
plus 3 minus 7/2 squared times 1/6 plus 4 minus 7/2 squared times 1/6 plus 5 minus 7/2 squared times 1/6 plus 6 times 7/2 or minus 7/2. That's a minus, not times. 5 minus 6 minus 7/2 squared times 1/6. right?
That's right.
You should,
And we can work it out. I really don't want to work with that.
okay.
I don't want to calculate all those differences, square them, and then multiply by 1/6, but we could do it, and we can figure out the answer. Instead, let's do a quick little theorem that'll help us calculate the variance a bit easier.
Okay.
And we're going to prove that the variance of x is equal to the expected value of x squared minus the expected value of x squared.
Yeah, no duh.
And we're going to show that that's the same thing as variance.
So brilliant.
So let's prove this. Alright, so the variance of x is equal to, by definition, it's equal to the sum, for all little s and big, that's why we won't bother writing that, of x of s
What?
minus mu squared times p of s. That's the variance, just using the definition.
Okay.
Right? That's exactly what we have written here. Okay, so this is equal to, first off I need to do is square this out. Now, if I have a minus b squared, what is that equal to?
A squared plus b squared.
Not even close.
A squared
Oh.
minus b squared.
A squared
Little
plus
closer.
2ab.
Actually, no, his was closer, I guess.
A squared plus 2ab.
A squared,
Minus
a squared plus
2ab
2ab
b squared.
plus b squared.
A squared minus 2ab plus b squared. Come on,
I
guys.
was close.
Well, I didn't want to just
I
go
was
to him.
closest.
What's a times a? A squared. What's negative b times negative b? B squared. What's a times negative b? Negative ab. What's negative b times a? Negative ab. Oh, you get that twice? Okay, so there's two of them.
Yeah, I had right answer.
4 things. Alright, so same thing now, except for instead of a, we have x of s, and instead of b, we have mu.
Why don't we just cancel mu?
So this is, you can't cancel them.
I don't know. I'm
Okay.
thinking zero again.
So we have x of s squared minus 2 mu times x of s plus mu squared. Oh, I forgot my sum. Sugar. Let's try this smaller. This is equal to the sum of x of s squared, and we need a parenthesis there. Okay, all that times p of s, right? You see that? I just squared that right here. Any confusion on the algebra? No confusion on the algebra?
No.
All right, what should we do next?
Simplify.
We should distribute the p of s in.
Distribute.
Oh, that's a good idea.
Yep.
All right, this is equal to. Distributing in the p of s, we're going to have the sum now of x of s squared times p of s minus 2 mu
B.
x of s times p of s plus mu squared times p of s. Right?
Yeah.
Now I'm just going to break these 3 inner sums into each of their own sums. I'm going to add up all these terms first, then all these terms, then all these terms. So this is equal to the sum of x of s squared times p of s. So that's this sum, plus the sum of negative 2 mu times x of s times p of s, plus the sum of mu squared times p of s. Good? So just taking all those terms and adding them up first, then adding up all these terms, then adding up all these terms. Doesn't matter what order I add in, order's commutative, or addition's commutative, right?
That makes sense.
Okay. Now let's figure out what each of these are. This is equal to, what is this the definition of?
Just of x.
No?
I expect value of x. With a square. There.
Yeah, this is the expected value of x squared. If you were to calculate the expected value of x squared, it'd be this exact thing,
Uh-huh.
right? Now let's look at this one. Over here, we can factor the negative 2 mu out of the sum.
Whoa.
Maybe we'll just do that first. Minus 2 mu times, now we have the sum of x of s times p of s. what is the sum of x of s times p of s?
Just X. Expected value of X.
This is just the expected value of x. So this whole term is just the same thing as the expected value of x. Wonderful. Now let's look at this one. Plus, we factor the mu squared out of that whole sum. So we have mu squared times the sum of all the probabilities.
So it's 1.
What's the sum of all the probabilities?
No.
Just 1. So that's just plus mu squared.
But a lot of expected values.
Yeah, a lot of expected values. So this is equal to the expected value of x squared. What's the difference between mu and the expected value of x?
There isn't one.
There isn't one. So minus 2 mu times mu again, which is mu squared, plus mu squared.
Which is
Why are we
mu-
writing mu
mu
if
for-
expected value different?
This is expected value of x squared. Mu is just the expected value of x. So this is equal to the expected value of x squared minus, if we have 2 mu squared and we add a mu squared, what do we have?
Mu forward, or 2 mu
That's a
forward.
negative.
1 mu
Whatever
squared.
it is.
This is a negative 2. If I have negative 2 of something, and then I add 1 of that thing,
Oh.
what do I have?
0.
Negative 1.
I have negative 1 of those things. I have negative mu squared,
Oh.
Which is exactly what we were looking for.
which is the exact same thing as the expected value of x squared minus the expected value of x all squared.
It's tricky.
And now, in figuring out the variance of this problem, rather than working out that horrendous algebra, let's just figure out the expected value of x squared for this problem, for rolling a die. So we're talking about rolling a die. Let's find the expected value of x squared. This is going to be 1 squared times 1/6. So 1 squared over 6, plus 2 squared over 6, plus 3 squared over 6, plus 4 squared over 6, plus 5 squared over 6, plus 6 squared over 6. And let's see what that equals. We'll just add them all up. 1 plus 4 is
5.
5, plus 9 is
14.
5 plus 9
14.
is 14, plus 16,
14
Like
plus
not
16.
30.
30, plus 25,
55.
plus 36.
55,
80.
93,
90.
91,
No.
96,
97.
86.
90, 98.
Guys, it's 91.
That's 91. That's what I said.
55
Plus
Plus
36.
plus 36.
91.
91.
Yeah, that's what I said.
So 91/6 is what the expected value of x squared is. Now, how do we figure out the variance for this? The variance is just going to be the expected value of x squared, which we now figured out is 91/6, minus the expected value of x all squared. What's the expected value of x for this problem? What's mu for this
3.5.
problem?
7/2.
7/2. So minus that squared, we're going to minus 49/4.
Jeez.
And now that's much easier than trying to deal with all the algebra of squaring a bunch of differences.
Did I get you the same answer?
Get you the same answer.
Broken.
So, much easier way to come up with the answer.
Yeah.
Right.
Pretty easy.
So, useful theorem for finding the variance. So that's the end of variance. That's the end of this chapter. You'll have a test next week. Be ready for that.
But the test isn't on variance.
No, variance will not show up on your test except for just proving this theorem and this one problem.
Okay? You're kidding, right?
We'll see.